Good afternoon, everybody. My name is Sean Patchett, and today I'm going to be your instructor, and this lesson will be on density altitude. Required materials for today will be the Rotorcraft Flying Handbook, your Robinson R22 POH, or your Pilot's Operating Handbook, and some pen and paper. This lesson is basically going to introduce you to density altitude, the factors that contribute to density altitude, and how to compute density altitude. Okay, so did you know that your body is carrying the weight of all the atmosphere directly above you? Aircraft performance is an extremely important factor in flying an aircraft. The information you will compute will essentially give you the performance limitations for your aircraft for the given conditions. This will help you in your decision as to whether the flight can be made safely or at all. Today, our overview is basically we're going to cover density altitude. We're going to cover the definition, air density, pressure altitude, temperature, relative humidity or moisture, and we're going to be doing some density altitude computations. So we're going to get started. The definition of density altitude is pressure altitude corrected for non-standard temperature and pressure. Pressure altitude corrected for non-standard temperature and pressure. So we're going to go ahead and get started with air density. Okay. Basically, a helicopter's performance depends on the lift production of the rotor systems and the engine power output from the engine. So we'll go ahead and write that up there. So we have lift performance and engine power output. Okay. Basically, air density is referring to the amount of air molecules contained within a given parcel of air. We have high and low density. So we have warm air that rises and creates a lower air density. It spreads those air molecules apart as it rises. So I'm going to write that one up. Warm air rises. And just the opposite, cold air descends, kind of compacts those air molecules and gives us a higher air density. Cold air descends. Air density affects both lift production and engine power output. So we're going to start off talking about your engine power output. Basically, with low density, you have less air molecules in the air-fuel mixture, thus giving you a less efficient fuel burn and less power. Big negative symbol there, for less, everything. Basically just the opposite. You have higher air density, you have more air molecules in the air-fuel mixture, you have a more efficient fuel burn, creating more power. With your rotor systems, lower air density, there's less air molecules flowing over that airfoil, creating those unequal pressures above and below. And there's also less air molecules to deflect. So you're basically talking about Bernoulli's principle with the airflow over, and you're talking about Newton's third law with the deflection of air molecules creating lift. And so less air molecules, there's less of both, so you're going to have less lift production. And again, just the opposite. With higher air density, you have more air molecules flowing over the blades to create a greater pressure difference between the upper surface and the lower surface. And there's more air molecules to deflect, so you're going to get more lift production. So as you can see there, warm air basically decreases both. Cold air, more dense air, increases both. A little review for that topic on air density. Define density altitude. What does air density refer to? What two things does helicopter performance depend on? How does low air density affect engine power output and rotor blade efficiency? All right, covers it. air density. Now we're going to talk about pressure altitude. Alright, the definition for pressure altitude is basically your height above the standard datum plane, which is a theoretical plane where atmospheric pressure equals 29.92 inches of mercury. Setting the altimeter to 29.92 inches of mercury, which is your ISA or your International Standard Atmosphere, that in 15 degrees Celsius. So if you set your altimeter to 2992 and read the indicated altitude, that's going to give you your pressure altitude. You can also compute pressure altitude. Basically, pressure changes 1 inch with every 1,000 feet of altitude. Basically, you just take your given altimeter setting. We'll say it's a different color here. So pressure altimeter setting is 3015. And you're comparing this to your International Standard Atmosphere, which is 2992. So you're going to go 2992 here. You're going to subtract. So you're going to go 3,291, 2. Those are going to cancel out. Here's your decimal point. 230 feet. That's your pressure altitude, or your value. And then you're going to go and apply that to your field elevation, and then calculate in your temperature difference. That'll give you your density altitude. But just for now, we'll just keep it with that, with pressure altitude. And basically, that gives you the air content for your particular elevation. So a little review over pressure altitude. Define pressure altitude. What is ISA, or International Standard Atmosphere, and what are its values? And how much does pressure change with altitude? I know it's kind of brief. I'm going to talk a lot more about this stuff, but I don't have a lot of time. And I'd like to be able to cover all this, so we're going to move on. Now we're going to talk about temperature. Temperature significantly changes air density. Basically, you have surface heating or convection. Basically, say here's your surface, right? And as that temperature rises, that heat coming off the surface wants to rise, and then it sort of dissipates or diverges, and all this other air, this cooler air up top, then comes down and wants to replace all of this air that is going upwards. So it's a big cycle. There's not going to be a void created. There's always has to be air somewhere, kind of like water. When you push water away, more water washes in. So that cooler air comes in and replaces that warm air that rises, basically giving you advection or wind along the surface here. That's another topic. So as warm air rises, like I said earlier, it spreads apart the air molecules, creating a lower air density. And this cold air that's descending compacts these air molecules down below and gives you a higher air density. So your 15 degrees Celsius or 59 degrees at Fahrenheit is your International Standard Atmosphere for temperature. Basically, with any, we'll mainly just talk about Celsius here, because that's what we use in aviation. For every 1 degree of temperature change in Celsius, it's going to be a 120 foot increase or decrease with your density altitude. So if you have a day that is 10 degrees Celsius. You're going to basically find the difference between that and 15, which gives you 5 degrees. So then you're going to go ahead and multiply that 5 degree difference by 120, which will give you 0, 0, 700 feet. And that's going to be negative because we have a colder temperature, more dense air, more performance, better performance. You can see that you get a lot more change and a much greater effect with temperature than you do with pressure. So a little review for temperature is how do higher temperatures affect air density? What is the atmospheric phenomenon called that affects air density in regards to temperature? How much does density altitude change with each degree of temperature? Alright, that's going to cover temperature for now. Now we're going to talk about moisture or humidity. Okay, so like I just said, moisture is also referred to as humidity. Today, there's two types of humidity. Today we're just going to talk about relative humidity. Okay. Basically, relative humidity is the amount of water vapor in the atmosphere, and it's expressed as a percentage of the maximum amount of water vapor the air can hold for a given temperature. So we'll just write Celsius and Fahrenheit there. So the maximum, it's expressed as a percentage of the maximum amount of water vapor the air can hold per given temperature. So perfectly dry air, no water vapor content in it, has a 0% relative humidity. And completely saturated air that can't hold any more water vapor has a 100% relative humidity. Warmer, lower density air can hold more water vapor. Those air molecules are more spread apart. There's more room for water vapor to move in. Colder, higher density air has less room. Those air molecules are more compact. There's less room for water vapor to move in. Saturation typically occurs when the air is cooled to the dew point, and moisture isn't too big of a factor for density, altitude, and performance, but it is a factor nonetheless. So basically, if you see, visible moisture out there, you just want to take into account that your lift performance and your engine power output is going to be affected a little bit, but not enough to where we have to compute for anything. So a little review for moisture is define relative humidity. What holds more vapor? Correction, what holds more water vapor, warm air or cold air? And when does saturation occur? That's going to do it for moisture there. Now we're going to just do a couple quick computations here. So I'm going to go ahead and do one for Troutdale's current conditions. So TTD there, we got 0704 is the temperature dew point, and altimeter setting is 3023, and our field elevation 39 feet. So we're going to do 15 degrees, because remember we're doing both comparison to international standard atmosphere here. So alright, 07, so that's going to be 018 degrees. We're going to times that by 120, so it changes 120 feet for every degree change. We have a difference of 8 here, so we're going to go ahead and do 0.61960 there. We'll go ahead and subtract here, 2, 9, 12, 3, those cancel out, decimal point, move it 3 spots, add the 0. So we have higher pressure, colder temperature, So we're going to add this number to this number. 0, 7, 12. We have 1,270 feet there. Now we're basically just going to add our field elevation to that. 6, 1, 3, 12. So 1,231 feet is our density altitude, negative. Because we have better performance with the colder air and better performance with the higher air pressure. So we're 1,231 feet below the standard datum plane, considering our temperature and our pressure. I want you to compute for Salem's current temperatures. We have 0807 and 3021 is your altimeter setting, and 214 feet is your field elevation. Okay. Give you a minute while I'm writing this up to go ahead and finish. I'm running out of time here, so I'm not going to compute it myself. Okay. So if your current conditions at your airport or wherever you're at is 15 degrees, 299 under 2, basically international standard atmosphere values, your density altitude is going to equal your pressure altitude. Because those are standard temperature and pressure. If you think of the definition of density altitude is correcting pressure altitude for non-standard temperature and pressure. Well, if they're standard, there is no correction to be made. Therefore, your density altitude is your pressure altitude. All right. And so with our review, when is density altitude equal to pressure altitude? So basically with this lesson, we covered the definition, air density, pressure altitude, temperature, relative humidity, and we did a couple computations here. And that is going to conclude my lesson for the day. Thank you.